Collisions and explosions are very brief events involving large, rapidly changing forces between the objects involved. Analyzing the motion of the objects during the event using Newton's second law is usually prohibitive, if not impossible. Fortunately, however, we can fruitfully use the principle of momentum conservation to relate the motion of the objects before the collision or explosion to the motion of the objects afterwards, bypassing the detailed motion during the collision or explosion entirely. This mini-lesson is the first in a series in which we will explore the problem-solving strategies involved in analyzing collisions and explosions. After a brief review of the underlying concepts and principles, we will then apply them to a specific collision problem. For a system of objects, the total momentum, capital P, is the sum of the momentum vectors of all of the objects. This is a vector sum. It turns out that the total momentum equals the momentum of the center of mass. In other words, if one imagines all the mass in the system concentrated as a single particle moving with the center of mass, then the momentum of that particle would be capital P. A system of objects is said to be isolated if there is no net force acting on it. With the concepts of total momentum and an isolated system in hand, we are now ready to state the law of conservation of momentum. It states that the total momentum of an isolated system is constant. Forces between objects in the system can cause momentum to transfer from one object to another, but they do not change the system's total momentum. Momentum conservation sees its greatest use in the study of collisions and explosions. Its applicability for these problems depends on the so-called impulse approximation. Collisions and explosions involve very large forces acting over very brief periods of time, causing momentum to be transferred among the objects in the system. Any external forces present, such as gravity, friction, and so on, generally don't have enough time or strength to appreciably change the momentum of the system during the collision or explosion. Therefore, the system can be treated as isolated during the brief period of the collision or explosion to a very good approximation. This means that the total momentum immediately before the event is equal to the total momentum immediately after. The total kinetic energy of a system of objects is the sum of the kinetic energies of all of the objects. However, unlike total momentum, the total kinetic energy is not equal to the kinetic energy of the center of mass. Collisions are generally categorized by whether or not total kinetic energy is conserved. A collision in which the total kinetic energy is the same before and after is called elastic, whereas a collision in which the total kinetic energy is not the same before and after is called inelastic. A special case of inelastic collision is a perfectly inelastic or maximally inelastic collision in which the colliding objects stick together upon impact, thereafter moving as one object. It's important to emphasize that not all inelastic collisions are perfectly inelastic. In summary, momentum is always conserved, to a very good approximation, in collisions and explosions, while kinetic energy is conserved only in elastic collisions. Okay, let's do an example. An archer shoots an arrow toward a target that is sliding toward her at 2.50 meters per second on a smooth, slippery surface. The 22.5 gram arrow is shot with a speed of 35.0 meters per second and passes through the 300 gram target, which is stopped by the impact. What is the speed of the arrow after passing through the target? And is it an elastic collision? For collision problems, it's useful to sketch the scenario both before and after the collision. Before the collision, the arrow is moving to the right at 35 meters per second, and the target is moving to the left at 2.5 meters per second. After the collision, the target has stopped, but the arrow continues moving to the right. Our goal is to compute the speed of the arrow after the collision, which is presumably less than its speed beforehand. To do this, we use the principle of momentum conservation. The final momentum of the arrow plus the final momentum of the target is equal to the initial momentum of the arrow plus the initial momentum of the target. Bear in mind that these are vector sums, which in one dimension means sums of signed quantities, with momentum to the right being positive and momentum to the left negative. Here we solve for v sub 1f, the final velocity of the arrow. All the variables on the right-hand side of this equation are given in the problem, so we can plug these numbers in and evaluate the expression to find the final velocity of the arrow, which is 12.8 meters per second. Note that this is indeed considerably smaller than the arrow's initial velocity of 35 meters per second, as expected. The lightweight arrow needs to give up a lot of speed in stopping the comparatively heavy, slow-moving target. Okay, now let's determine if the collision was elastic. Clearly not, since both the arrow and the target slow down as a result of the collision. But to make it concrete, let's calculate the kinetic energies. The kinetic energy before the collision is the sum of the kinetic energies of the arrow and the target before the collision. Plugging in numbers gives an initial total kinetic energy of 14.7 joules. After the collision, the target has no kinetic energy, so the total kinetic energy is just the kinetic energy of the arrow, which works out to be 1.84 joules. Since the total kinetic energy is less than the initial total kinetic energy, the collision is inelastic. That said, since the two objects did not stick together after the collision, it was not a perfectly inelastic collision.